Hello, welcome to the chemical bond series. Today we shall discuss about bond energy, bond length, and bond angle in covalent molecules and ions. Now, the bond energy, bond length, and the bond angle, they are very important part of the shape of the covalent molecules and ions. So to have an idea how the bond energy varies among different types of bonds, how the bond length varies with the different types of bonds, and so also the bond angles. Let us study some general rules. Now, before that, let me introduce what is the difference between bond dissociation energy and bond energy. Bond dissociation energy is the original aspect of bond energy. Is the amount of energy required to break 1 mole of a particular type of covalent bonds in gaseous state to atoms or radicals by homolysis. Homolysis means one electron shift at either 0 Kelvin or standard state. It's called bond dissociation energy. It means the first BD, because if there are successive bonds of identical type, you want to break it successively, then the energies will be different. So the first bond that you are going to break, the energy required to do that in the gaseous state to form atoms or radicals, that is called bond dissociation energy. And for symmetrical molecules, the first BD is usually called the BD. For example, ethane, there are 6 CH bonds of identical type. So the first CH bond breaking, that is called the first BD, or in general simply BD. But if you take the average of all the 6 BDs, BD1, BD2, BD3, and till all the CH bonds are broken down, then we take an average of all these values. These values are different, slightly different, because by the loss of one or more hydrogen atoms, the net force governing the entire molecule becomes different. So the next energy value will be different. So that is called the average bond energy, or simply bond energy. And whatever data you find in the tables, they are all average values. But BDE is the real original. And I tell you what is called the homolysis or homolytic cleavage, shown by a fish hook arrow mark. A fish hook arrow mark, not a normal arrow. A fish hook arrow represents one electron shift, so that respective groups or atoms gets back its own electron. So they form atoms, or if it is a group of atoms, it is called a radical, but contains an unpaired electron. Right? For example, ethane, the first CH bond breaking requires this much of energy. That means the BDE of CH in ethane, you have to mention that, is 423 kilojoules per mole. Is not the same if you break the CH bond in another molecule. It might be slightly different, we'll talk about that. And when you take so many values and take an average, then yes, CH single bond energy is 410 or 415 or something like that. But this is the first BDE is really called the BDE. Similarly, CH3F, there is only one carbon-fluorine bond, and to break that, to form fluorine atom and methyl radical, both of them have unpaired electrons. This much of energy is required. So BDE of CF bond is this much, 481 kilojoules per mole. So also, this is benzene. The CH bond requires much greater energy than the CH bond that needs for ethane. We will know the reason why just after a bit. As I have already told you, bond energy is usually the average of so many bond dissociation energies, successive bond dissociation energies, BD1, BD2, BD3 of identical type. Ethane means all the 6 CH bonds of ethane. Methane means all the 4 CH bonds of methane. Propane means all the 6 CH bonds in the two terminals are of one type, and the middle CH2 is of another type. It has got different values. So that what you will learn in organic is called the secondary carbon atom in the middle. There are two such hydrogen atoms. So that you have to make an average of these two. So it's really very interesting. So as a beginner in chemical bonding, I would not like to drag you more to the organic area, right? But for diatomics molecule, diatomics as we call it, N2, O2, H2, HCl, HBr, only two atoms, then there is no average. The bond dissociation energy is same as bond energy. But usually bond energy term is applied to average values of a particular type of bond. For example, HH in H2 is this much. So that is no average concept here. In HCl, this much. But in methane, there are 4 BD values and the average is this much. Now, I have given you the data for your appreciation. The data that the first CH you break, you need little less energy. The second one, much greater. Third one, again less. And the fourth one is the least. And if you add all these and take the average, you will get the average CH bond energy in methane is 415.75, right? It may not be same as the CH bond energy in ethane. It may be different because that is the average of 6 CH bond energy. But once we say BDE, then that also needs which molecule? Which molecule? CH, okay, CH. But which molecule? Is it ethane? Or is it methane? Or is it benzene or whatever? So then the slight variation in the bond energy can be explained. And in similar types, for example in ethane, for example in alkane, if you make an average of all the types of CH bonds connected to a sp3 hybridized carbon, then you can get an idea as the average bond energy value for a CH bond bonded to a sp3 hybrid carbon. But if you are very, very meticulous, then even in alkanes, you will have to find the different types of carbon atoms, 1 degree, 2 degree, 3 degree, and so on. We'll be doing that. Similarly, the average bond dissociation, average bond energy of OH bond in water, because there are two OH bonds. First one will need this much, second one will need this much. Widely different, and their average value is 461, and we take the bond energy of OH is this one for our calculation purpose. In thermodynamics, you will be using that to find the enthalpy change of a reaction, taking the bond energy data. You'll be knowing, if you are not conversant in thermodynamics, you'll be using the bond energy data to find the enthalpy change of a reaction. Now what I was saying is that this OH bond energy average will not be the same if you find the OH bond energy in another compound. For example, in methanol, ethanol, or in phenol, the same OH bond, but the bond energy will not be different. Although in methanol there is only one OH bond, but that will be the BDE, there will be no average in that case. There is only one OH bond. That will be different from this. That depends on to which other group it is bonded. For example, in phenol, that OH, that O is bonded to an sp2 hybridized carbon. In ethanol, that is bonded to a sp3 hybrid carbon. So later on we'll know. As the hybridization of the neighboring atom changes, then also the bond energy will slightly vary, sometimes drastically. Now, please allow me to involve a theory which is usually not invoked while discussing the bond energy data, comparing the bond energy data, but I felt like using my experience in teaching infrared spectroscopy in higher level to bring in the alternative Hooke's law to explain the trend in bond energy data. Please bear with me if I am using this unwanted, but believe me, you will find a bit of logic in it, although there will be some deviations at places. We will feel sorry about that at that time, but if most of the trends in bond energy variations among different types of bonds can be explained by this principle, then it is well and good. I will definitely caution you that if you don't find this in any other source, don't be surprised. And also don't take it as an absolute rule of thumb to to assess the relative bond energy data. Now see, a covalent bond, may it be a single bond, double bond, or triple bond, is taken as a bond oscillator. It is like a spring, either a very light spring or tough spring or very stiff string, and the stiffness of the string is determined from its K value, the force constant. If you have studied the Hooke's law, the original Hooke's law, when you stretch a spring, from there you have this equation. This is another version of the Hooke's law used for studying the wave number of the bond oscillator. Any bond between two atoms, that bond is believed to be a simple harmonic oscillator which is vibrating at its natural frequency, right? So that wave number of that particular oscillator, bond oscillator, can be approximately found by using this modified Hooke's law, that is nu bar is equal to 1 by 2 pi c. C is the velocity of light, K is the force constant. If the bond spring is stiff, then K is large, bond is stronger, bond energy to break down is more. And if the mass, the reduced mass, of course this term might be unknown to you, reduced mass is important when the two atoms are different, carbon oxygen, carbon nitrogen. That reduced mass mu is m1 into m2 divided by m1 plus m2. So take the two masses of the two connecting atoms, multiplied in the numerator and added in the denominator, and that gives you the reduced mass. So more is the reduced mass, less is the nu bar, and you know nu bar, which is wave number, is directly proportional to energy. So if bond energy is nothing but hc nu bar, so more is the nu bar, more is the bond energy, right? So the bond energy is directly proportional to the stiffness of the spring, how stiff the spring is, bond spring is, K value, the force constant of the bond oscillator, and inversely proportional to the mass, reduced mass, right? So we can apply this to a large extent to explain. Of course, this is not included in your syllabus, but I have introduced this concept just to explain in a more logical manner, of course, submitting at places where we find even the Hooke's law is not able to explain the anomaly, right? And a single bond and a double bond and a triple bond have, uh, you know, different K values. The double bond is nearly the double and the triple bond is nearly the triple of a single bond. And in dynes per centimeter, it is approximately 5 into 10 to the power 5. This is 10, this is 15 for triple bond. Of course, approximately. And it varies. If polarity will increase in the bond, then 5 can be 5.2, 5.3, 5.4, 5.6. It can vary. So also the 10, 10.2, 10.3, 15, 15.2, 15.3. So this is approximately, double bond is twice, triple bond is thrice of a single bond. So we shall be often using this to explain, but never ever use in your examination or talk to anybody about this much, right? Let us set up a general principle that triple bond is stronger than double bond. Double bond in turn is stronger than single bond. And for that, you have to take an identical atoms. N triple bond N with N double bond N with N single bond N. Similarly, C triple bond O, that is a carbon monoxide, C double bond O in a compound, carbonyl compound, C single bond O like alcohol, whatever. So that is the trend. Not all double bonds are stronger than all single bonds. It's not that all double bonds are stronger than all single bonds. It's not like that. But identical, if they are identical atoms, yes, it is. But the triple bond, any triple bond, are the strongest. Stronger than all double bonds? Obviously, stronger than all single bonds. But the double bond, I'll give you an exceptional case where N double bond N, the bond energy is 418 kilojoules per mole. And these single bonds, HH, HF, CF, OH, these single bonds involving small hydrogen atoms, they are stronger than even a double bond N, where there is no polarity and no hydrogen atom. So there are exceptions, no doubt about it. Now let us focus our attention on single bonds. Let us give our focus on single bonds now, right? Only single bonds. Some of these generalizations that I will be sharing with you might help you in your examination. The first point is single bonds involving small or the smallest hydrogen atom with a second period element from carbon to fluorine, because the covalent bonds are with the electronegative elements in the right portion, the P block, carbon to fluorine. They are also small. Is stronger than single bonds with the same element, that is a fixed element, with other elements from carbon to nitrogen. What I wanted to say, of course with one exception. What I wanted to say, supposing you compare CH with CC, CN, CO. C is common. And the other atom changing from carbon to fluorine. This time fluorine is an exception. So CH will be stronger than all other bonds involving carbon with the second period elements. Why? The exception carbon-fluorine bond is even stronger than CH bond. That is the only exception. I will talk about that later. Similarly, NH, N is fixed, is stronger than NC, NN, NO, even NF. OH, O now is constant. OC, ON, OO, OF. All are weaker, OH is stronger. FH is stronger than FC, FN, FO, FF. So that is a generalization. The reason is that H is the smallest atom and the reduced mass, this is the least. So the energy is maximum. That means any bond, single bond involving hydrogen atom is usually stronger bond because of the reduced mass effect. Smaller reduced mass, nu bar is more. But you can't compare any single bond involving hydrogen with any other single bond not involving hydrogen. The generalization I have shown that the same carbon or nitrogen or oxygen and fluorine remaining fixed with hydrogen and other bonds with the same fixed element with other elements have to be compared. Invariably you will get this. I will show you the data table. CF, why CF is stronger than CH? It's because polarity also is important. The difference in electronegativity is not much. Carbon is 2.4, hydrogen is 2.2. But carbon is 2.4, this is 4. So a huge difference in electronegativity makes the bond polar. If the bond is highly polar, plus delta, minus delta, they attract each other. So the spring becomes stiff. The K value increases. May it be single bond, but still then, over and above 5 into 10 to the power 5 dynes per centimeter, it increases more. So there are two mutually cancelling effect. Mu is less for CH bond, no doubt. But if the K contribution is more, because of the polarity, K increases to a greater extent compared to the decrease in mu as hydrogen is a small size atom. The dominant effect is K here because of polarity, not mu, for which CF bond is stronger than CH. And if you look to the table to just have an idea, I have just prepared a table for you to have a glance at the different values. These bonds which involve hydrogen, they are higher, kilojoules per mole, 4. The only unfortunate is NH, 391. I'll talk about it later. Otherwise, all bonds involving hydrogen are the highest. I mean, are very high. And in fact, FH is 565 because of the polarity factor. We're not talking anything about bond length now. Talking only about bond energy. But these are not involving hydrogen. These are not involving hydrogen. From here to here, you will find all of them are lower than this, excepting NH. The general idea that the bond, single bond involving hydrogen are stronger, excepting NH. And the single bond not involving hydrogen is weaker, except CF bond, polarity factor. All others are 146, 154. HCl is 427, okay. NF because of the polarity factor. NF is 272 because we'll discuss about these reasons very soon. Now this is the main source table from which I have copied. These are all in a mixture form, in a systematic form, no doubt, but all are there. But I have singled out a few to show you that how the reduced mass of hydrogen, reduced mass of the entire bond oscillator contributes to significant extent to make those bonds involving hydrogen stronger than those which do not involve hydrogen, barring a few exceptions, and the regions also we will try to explore. Now, the second point, polarity effect. I was saying that in a period, if you go from one to the other in the p block in a period, keeping one atom fixed and changing the other atom in that series, in that period, you will find the polarity of the bond will increase. More is the polarity, more is the force constant. Because of the attraction between opposite poles, plus delta, minus delta, the bond oscillator will be stiffened. So K will be more. So, supposing we keep hydrogen constant here and change the other atom from carbon to fluorine in a systematic manner in a period, we are expecting, because the polarity goes on increasing, the value, the bond energy value should go on increasing. Yes, it is largely true, but there is one anomaly. That anomaly, you have to remember that NH, instead of being second from the lowest, instead of being second, it is itself the minimum. Then others are according to our expectation of polarity. Now, why NH bond is the weaker? You can have a look. The NH, here it is NH 391, while CH is here 413. The weakness, although the polarity is higher than CH, but it may be due to the dominating reduced mass, because nitrogen has a greater mass than carbon. Whatever the polarity factor that is responsible to increase its bond energy, that is negated and dominated by its greater reduced mass in the denominator. That's the reason why, maybe the reason why, NH bond is the weaker. Similarly, if you keep the carbon fixed and again change from carbon to fluorine, then you will expect the same trend due to increase in the polarity and hence force constant of the bond oscillator. But again, the same anomaly, the CN bond is the weakest. You can verify that. CN is here, is 305, and CC is much greater. CC is 347, 305. Not much greater, but greater. So that may be due to the dominating effect of the reduced mass of CN bond compared to its polarity, which increases K. Then another aspect. Between homonuclear bonds, the two atoms are same. It may not be a homonuclear diatomic molecule. It can be a part of a molecule. For example, N single bond N is not a molecule. C single bond C is not a molecule. But O single bond, it's not, but only FF is a molecule, fluorine. In all other cases are a part of a structure. Doesn't matter. So we expect, since they are not polar, K is not a factor. It's not polar, so K is not a factor. But reduced mass is a factor. It is going from left to right, the reduced mass increases. And moreover, the number of lone pairs also increases. Because of the repulsion between the lone pairs in the adjacent atoms, K value, the bond oscillator becomes weakened. The stiffness reduces because of repulsion. So K value also decreases. So there is a cumulative effect. K value in the numerator decreases due to increasing number of lone pairs. And at the same time, mu increases due to increase in mass. So that makes drastically decreasing carbon-carbon. You can find carbon-carbon is 347, nitrogen is 160, but there is an anomaly here. That is an interesting anomaly here. We expect both mu wise, mass, reduced mass wise, and lone pair repulsion wise. This should be the minimum bond energy, but unfortunately, oxygen-oxygen bond has the minimum bond energy. You can have a look. OO is only 146, while FF while FF is 154. 146 is less than 144, 154, less, convincingly less. And I have raised my hands. I will not adopt to any speculation method. Here is the place where I submit. We can't apply the Hooke's law to explain in any way that both wise, K wise and mu wise, it is supporting that the FF bond energy should be the least. But actually OO bond energy is the least. So that anomaly, you must remember that. That is the reason why I am highlighting this in a dedicated lecture. Coming to the trends in the groups, the anomalies are very, very uncommon, because as in a group, as the size increases, the reduced mass mu also increases, and polarity also decreases, the electronegativity decreases. So the numerator K factor decreases. As the polarity decreases, the bond becomes less and less stiff, and mu increases. So both support the decrease in bond energy, and that happens in most of the cases, barring the homonuclear bonds. A few homonuclear bonds of nitrogen, oxygen, and halogen family. These are the three families where you will encounter anomalies among nonpolar bonds. I'll tell you why. First let us take up HF, HCl, HBr, HI. As expected, the bond energy is in this order because the size goes on increasing from fluorine to iodine. So expected order and actual order, they are same, no anomaly. But among homonuclear bonds, these are homonuclear diatomics, they exist as diatomic molecules, that there is an anomaly. The expected order according to size or mass, reduced mass, and they are not polar at all, so they are non-polar. Here both mu and K factors are there, but here there is no K factor, they are all non-polar, right? So but the reduced mass would expect this to be the order, but actual order, the strongest bond energy is chlorine-chlorine, and ironically fluorine-fluorine, which is expected to be the strongest bond, is now the third highest. It is just after bromine-bromine. What has happened to fluorine-fluorine to make it third in the hierarchy? It is because of its small size. The lone pair repulsion factor is so pronounced that the reduced that decreases the force constant K in the numerator. Even if it has got the lowest reduced mass, mu factor is favorable to make it stronger, but the reduced K factor, due to strong repulsion between the three lone pairs in each atom being in close proximity, that makes this difference. Now in all other cases like OH, SH, SEH, TH, where H is constant and you go down the group, expected and actual order the same. Even in carbon family, the diatomic bonds, they also have the same trade, no anomaly like halogens. Fluorine is a very small size atom and there are three lone pairs, and carbon family doesn't have a lone pair, so such anomaly is not expected. Not expected also. So also found the same. But nitrogen and oxygen family, they do have lone pairs. So that is the reason why expected bond energy trend is this. Nn should be the highest, but actually Nn is the second highest. PP takes the lead. Why PP takes the lead? It is because N is a small size atom And the lone pair repulsion makes the K factor little more dominating than the mu factor, for which it only exceeds, only PP exceeds NN, not that NN could go behind arsenic and antimony. So there is only a reversal between these two bonds because of the lone pair repulsion factor. Same thing happens in oxygen family. We expected oxygen to be the strongest bond, but actually it is the second strongest bond. Sulfur takes the lead because of the small size lone pair repulsion. In all cases there are lone pair repulsion, but because of the small size the repulsion is more pronounced. That makes the K factor more dominating. Only K factor means K is reduced. K factor is more dominating. Doesn't mean that K is more. K is less to the extent it is less than sulfur. But still the reduced mass effect is there so far other bonds are concerned. Right? I have explained all this. So there is no need to read and waste time. Let us talk about double bonds. Whatever little logic that I wanted to share with you for analyzing these single bonds, I have done it. So to sum up, that if in a period polarity increases, then the bond is expected to be stronger. But anomalies are there. You remember CN in the C category and NH in the H category, they are the weakest type. And homoannular bonds, the trend is the reverse. It's gone decreasing, but you found an anomaly. That FF bond is not the weakest. It is the OO bond is the weakest. Right? And among groups, it's very cool, excepting the homoannular bonds in the halogens, in the oxygen family and the nitrogen family, where in the halogens the fluorine goes to the third position, and in oxygen sulfur goes to the first position, oxygen goes to the second position, not as to the third, and in nitrogen family nitrogen also goes to the third position. Let's talk about double bond. Same polarity. More is the polarity. If in a period you go from C double bond C to C double bond N to C double bond O, then you expect the polarity will be more, even if all are double bonds. But they gain the force constant K of double bond, which is approximately 10 into 10 to the power 5, will go on increasing. And as polarity increases, the force constant K increases, and hence that factor is dominating, although the mu factor is not favorable, but the K factor is dominating. That makes the bond stronger expected, as well as we found the bond energy to be true. And in homonuclear bonds of double bonds, where this is a real molecule, O2, although this is a paramagnetic molecule, the bond is not like this, but well, yes, bond order is 2 for oxygen. But this is a part of molecule N double bond N, C double bond C. So that we expect, as like single bonds in homonuclear diatomic bonds, so this goes on decreasing because of both the mass effect as well as the lone pair repulsion effect. But again there is an anomaly. Here O double bond is stronger than NN. There is no FF double bond, so that is not in the list. F is monovalent. So here single bond wise OO was the weakest, even weaker than FF, but double bond wise NN is the weaker. I'm sorry, I'm not able to use the Hooke's law here, like the case for oxygen being the weakest bond among single bond category among homonuclear diatomic bonds. Here we can't say, because mass wise this should be the weakest bond, And also the lone pair wise, it should be the weakest bond. But it is stronger than NN, but weaker than CC, no doubt about it. That is okay, but why there is a reversal in this? I cannot have any interest to make a bluff. Now, I have shown it here. Triple bonds are really superseding. 941, 839, they are the strongest among all covalent bonds. But double bond, see, N double bond N and O double bond O. I was just saying that O double bond O, which is supposed to be the weaker, is stronger than N double. It's 495, this is 418. Now let's talk about triple bonds. Same polarity effect. CC, CN, CO. More is the polarity, even if the approximate K is 15 into 10 to the power 5, but there is an increase due to increase in polarity, stiffness of the bond oscillator. So here there is no anomaly. If you see C triple bond O, which is itself a neutral molecule, carbon monoxide is 1072, while C triple bond N is 891, C triple bond C is 839. So expected and actual they are equal. But again I am sorry, while homoannular diatomic bonds, it is expected because of the lone pair and because of the greater mass, this is expected to be weaker. But actually N triple bond N is stronger than C triple bond C. I'm sorry, I cannot use Hooke's law here to explain. N triple bond N is 941 while C triple bond C is 839. Convincingly N triple bond N is greater. I think the way I'm presenting before you all this, to make sure that you remember the trend, the anomalies. Hooke's law is unimportant for your examination. Now, before we have another session for bond length and bond angle, we close this session. Let us talk how the nature of hybridization of the central atom to which a particular atom is bonded is important to alter the bond energy. For example, this CH bond where the H is bonded to a sp3 carbon, and this is sp2 and this is sp. More is the S character, stronger is the bond. S means closer to the nucleus. So the bond will be lying stiffer, closer to the nucleus and become stronger. The force constant will be more, right? So I have the data with me. CH bond energy for say a propane, for example. CH, this is sp3 hybrid carbon, is 410, average bond energy 410, while the same CH bonded to sp2 hybrid carbon is 435 and sp hybrid carbon is 523, and the BDE, the first dissociation, is still greater, 423, 456, 547. So the more is the percentage of S character in a particular bond, may it be CH, may it be CC, whatever. This is CH compared between CH bonds, but more S character means stiffer, stronger bond. And stronger is the bond, let me tell you in advance, of similar category, shorter is the bond. For similar category CH we're talking of, stronger is the bond, shorter is the bond. Bond length is less because the S character will reduce the distance between the two nuclei, because more is the S character, so bond length will be the least. And you can find here this CH bond is 1.10 angstrom, this is 1.09 angstrom, little less, and this is 1.06 angstrom. So they have been studied with convincing proof that the bond length goes on increasing as the bond energy goes on increasing in a particular type of series. Now, another aspect I was talking in the beginning is the BDE, how it changes with the number of hydrogen atoms bonded to a carbon. For example, we find the same CHBD in ethane, and in the middle CH of propane, and the middle CH of isobutane, where there is only one CH. This is called a, you will know later in organic chemistry, this is called a tertiary carbon, this is a secondary carbon, and these two are primary carbons. You will know about it. If there are 4 hydrogen or 3 hydrogen atoms attached to a carbon, it is called a primary. 2 hydrogens, secondary. 1 hydrogen, tertiary. And we are talking about the BDE, not the average. So the BDE of CH bond in methane is the highest. In ethane, it is less, convincingly less. In propane, the middle one, the secondary CH, is still less. And in isobutane, it is the least. CH is 403. And this can be explained because we are explaining the bond dissociation energy as a homolytic cleavage, homolysis. I told you one electron shift shown by a fish hook arrow mark, giving you radicals or atoms. So that, you will later on know that more branched is the radical, more is the stable radical. So after losing this bond, this will form a 3-degree radical, tertiary butyl radical, that is much more stable than this is isopropyl, a secondary radical, and this is a primary radical, and that too, this is the least stable, right? All about this are the domain of organic general chemistry. We are not supposed to learn, know about the basics of organic chemistry. Forget about it, but yes, it has got a solid explanation as to why there is a slight decrease in the bond energy of the same type of bond CH as the number of carbon atoms attached to that particular carbon becomes less and less. 4 maximum, 3 less than that, 2 still less, 1 least. Now I have a question for you. Why the HH bond energy is smaller than HF bond energy? You can answer it. While HH, the 2 atoms are so small, but it is non-polar. Fluorine is undoubtedly size-wise, it is more, but mass-wise it is much greater. It is 19 times greater than hydrogen atom. So we are interested in the reduced mass. So even if the reduced mass of HH bond is very, very less compared to the reduced mass of HF, but because of polarity, it is a highly polar covalent bond, the K factor is dominating here, much greater, because here it is merely a single bond, non-polar single bond. It's 5 into 10 to the power 5. But this polar bond makes K much greater. So the lower mu factor for HH bond is dominated by the greater K factor for HF bond, which makes the HF bond stronger. And if you can have a look to the HF bond, HF is 565 while HH is 432. See the difference, right? Now we talk about let us complete this bond length and bond angle another 10 minutes. That will make this particular chapter closed. Bond length discussion is not that very intriguing or very difficult. It is easier. Now for a particular type of bond, greater is the bond order, means bond energy, less is the bond length. Bond length and bond order, they are inversely related. Stronger the bond, shorter the bond. Among a particular type, for example, carbon-carbon triple bond is the strongest bond, but bond length is the minimum. The bond length, the data you will find here, all data will you find C triple bond C is 120, while C double bond C is here. C, yes, it is 134. It is greater. And C single bond C, yes, it is 154. So 120, 134, 154, this is in picometer. So what I was saying here is greater the bond order or bond energy, lesser is the bond length. And also, if the S character of a bond is more, which made the bond stronger, that same reason will make the bond shorter. Now, I have already told you this example. Because this is a stronger bond, the bond length is less, CH bond. Because it is the weakest bond among the three, the bond length is greatest, right? So, the percentage of S character also contributes or decides both the bond energy as well as the bond length. Similarly, let us compare the CC, single bond length, CC, this one, highlighted by an arrow mark. Same CC, but this is sp3. S character is least. This bond length is more, 153.7 picometer. Now, this CC bond is between sp2 and sp3. More is the S character, more is the bond energy, less is the bond length. It goes on stronger. As the bond goes on stronger, the bond length goes on decreasing. And now this is butadiene, this is sp2, this is sp2. So more S character, and there is a resonance. If you have not studied, forget about it. So there is a partial double bond character because of resonance, and moreover, this is sp2, the sp2. So more S character means the bond is stronger and the bond length is lesser. And this is sp. sp has a 50% S character. Even if it is sp3, the bond length is the shortest, sp. So all are carbon-carbon single bonds, but bond energy wise, I have no data. This data, this is the minimum CC bond energy data, and this CC is the maximum one, but I have the discussion on bond length, so it goes on decreasing as the percentage of S character goes on increasing in a bond, the bond length goes on decreasing. That's it. Now, in a group, the bond length decreases in a systematic manner. There is no anomaly as we encountered in bond energy. Such anomalies will not be found in bond lengths. They do not have any Hooke's law factor to govern, the K factor, the mu factor. The only size factor is important, not the mass, size. So down the group size increases. For example, in the halogens, bond energy there was anomaly. Fluorine coming to the third position. But no. In the bond length, FF is the shortest and II is the longest. You can verify that. FF is 142 picometer. CL is 199. BR is 228. II is 267. So there is no anomaly. It is something to do with size, not with mass or the force constant of the bond oscillator. It's not talking of bond energy, right? Similarly, HF, HCl, HBr, HI, as the halogen goes on increasing in its size, the bond energy decreases, no doubt. That there was no anomaly. There also, here also, the reverse is the trend. HF is the shortest bond and HI is the longest bond, and no anomaly. In a period, as the size goes on decreasing, the bond length also is expected to decrease. So, in bond energy, there was an anomaly. We were discussing which factor dominating over which factor in the Hooke's law and tried to understand, remember the anomaly, but here there is no anomaly. As the size goes on decreasing from carbon to nitrogen to oxygen, fluorine, the bond length goes on decreasing. You can testify that from the table. But again, only for one time I am saying sorry, that in bond energy among homoannular diatomics, there was an anomaly that could be explained. That could not be explained. That was a sorry factor there. because FF should have been the minimum energy, both wise. Lone pair repulsion wise and reduced mass wise. Here also in bond length, as size goes on decreasing across a period, we are expecting that nitrogen should be of longer length than OO, but OO is of longer length. You can have a OO single bond length 148 and NN is here is 160. So OO is 146. I'm sorry, OO is 148 and NN is 145 here. Bond length is here, I'm sorry. 148 and 125. So why OO is a longer bond than NN, although individual size-wise nitrogen is greater size than oxygen. So nobody knows. My hearts are up. Sorry again. And finally, bond angle, another few minutes. Bond angle depends on the hybridization. Hybridization is sp, like BeCl2, it is 180 degree. If it is sp2, 120. If it is sp3, 109 degree 28 minutes, approximately 109.5 degree. But slight changes in the normal expected angle, it is due to the presence of lone pair. And from the VSEPR theory, lone pair bond pair repulsion is greater than the bond pair, right? That makes ammonia smaller than the tetrahedral angle in methane, and water still less because of the presence of two lone pairs. That The third factor which is important is the electronegativity of the central atom. If the central atom varies, the ligands, the peripheral atoms, which are sometimes called ligands, they remain fixed, and the central atom goes on changing from one to the other in a group, then the electronegativity also decreases. So as the electronegativity decreases, these bond pairs goes further away from the central atom. If they are closer to the central atom, then the repulsion between the bond pairs is more, so the bond angle is more. We are talking about bond angle now. We have finished bond energy discussion, bond length discussion, now bond angle discussion. So less is the electronegativity, less is the bond angle. As you go down the group, bond angle decreases. Why? Because these bond pairs, they go further away from the central atom, and the repulsion between them decreases, bond angle decreases. I'll give you two examples. In the family, hydrides of chalcogens, water, S2S, S2Se, that is hydrogen selenide, hydrogen telluride, you find there is a decrease in the bond angle. Here, water, it is close to tetrahedral because oxygen uses sp3 hybrid orbital, so it should be 109.5 degree, but because of the presence of two lone pairs, there is a little more separation, and the bond angle is 104.5. But all others are close to 90. Even if they are close to 90, there is a decrease because of the reasons I explained. Similarly, in the hydrides of nicogens, nitrogen family, ammonia is 107. Nitrogen uses hybrid orbital, but one lone pair makes it little less. But these, I tell you that the third, fourth, fifth period elements, they have larger energy. So they cannot use hybrid orbitals to overlap with 1s orbital of hydrogen. So there is an energy mismatch between the hybrid orbitals of sulfur, phosphorus, this third period, fourth period elements, and the hydrogen's energy. So therefore, you will not find any molecule involving hydrogen and a third period element like phosphine, like S2S, like arsine, angle exceeding 100 degree or even coming close to 100 degree. It will be in the vicinity of 90, which means that the central atoms are mostly using the pure p orbitals which are lying perpendicular to each other. And there is a minor change, decrease, and this decrease is explained because these pairs they go a little further away from the central atom. With the decreasing electronegativity, the repulsion slightly decreases, the bond angle also decreases. Right? In case of water and ammonia, the lone pair they remain very close to the central atom because they're highly electronegative. So the repulsion is maximum. You can explain that even without invoking hybridization. You can also explain why in water and ammonia the angles are so large because it's highly electronegative. Oxygen is 3.5, nitrogen is 3. In all other cases, the central atom has a lower electronegativity, so they are farther away. But you know, oxygen and nitrogen, they use hybrid orbitals. Now the last point is about the variation of the peripheral atoms or the ligands, keeping the central atom fixed, and that too an element from third period, for example phosphorus. And these are the varying atoms, say chlorine or bromine or iodine, right down the group. So as the electronegativity of peripheral atom goes on decreasing down the group, conversely as the size increases, then bond angle also increases. There it was decreasing bond angle because here the central atom was varying, but here the peripheral atoms are varying. Central atom is also big, it's not a second period, it is a third period element, and the peripheral atoms also are big and are changing. So that is a different theory comes into picture that makes the bond angle greater than 90 degree. So the theory that tells you why the bond angle is greater than 90, on one hand I was saying phosphorus, they are incapable to use hybrid orbitals, right? There is a lone pair here. So sp3 hybrid means it would have been 109, in the vicinity of 109. So while we're saying that, we are saying that it will be 90 degree because they will be using pure p orbital, right? But the angle is much greater than 90 because of a theory called NBEPR theory. Just like VSEPR, we have another theory called NBEPR. What does it mean? Non-bonding electron pair repulsion. You know, these bulky atoms, they are electron clouds. They are close in space. So this is called a space repulsion or steric repulsion between the bulky atoms. So that is called non-bonding electron pair repulsion. Because of the repulsion of the electron clouds in space, there is an increase in the bond angle. And that too, it is more than 90, and it goes on increasing if you change from one atom to the other with increase in size. Chlorine, bromine, iodine increase. Similarly, arsenic chloride, arsenic bromide, arsenic iodide, there is an increase. All are greater than 90 because of this NBPR, and among them, as the size increases, electronegativity decreases, the bond angle increases. So we have another simple, a very approximate equation. It's not a 100% rule of thumb, but Schumacher and Stevenson have given an empirical equation based on observation that bond length between two atoms can be approximately found from the covalent radius of atom X, covalent radius of atom Y, and there is a constant 0.09 into the difference in electronegativity. And this is an angstrom unit. And what is covalent radius? It is half of the homonuclear single bond. For example, covalent radius of carbon means carbon-carbon single bond length by 2. Covalent radius of chlorine means single bond length of chlorine-chlorine bond length by 2. So that is called the covalent, pure covalent radius. It's not an approximate one, it's pure covalent radius. You have to take the homoannular diatomic bond length by 2. So this equation we have used in a problem self-assessment question. Carbon-carbon, chlorine-chlorine bond lengths are given. Electronegativity of carbon and chlorine are given, and you are asked to find out what is the expected carbon-chlorine bond length. So in angstrom is 1.54 by 2, that is the covalent radius of carbon, and 2.43, I'm sorry, this should be 43. 43 by 2 minus 0.09, the electronegativity difference. And the answer comes 1.99 against the actual value of this is which bond? This is the CCl bond. We have the data is 1.99. This is in picometer, 1.99, and we are getting also 1.99. Oh, sorry, CCl. Yes, it is 1.99, and we are also getting 1.99. So by chance, it exactly matched, but in most cases they are approximate. Schumacher and Stevenson rule. This finishes our program, and I tell you, there will be an interesting discussion on Bend's rule in covalent molecules. That is an alternative rule to VSEPR theory to explain many interesting bond angles, bond lengths, which cannot be explained by the VSEPR theory. Sometimes it supports and it is an alternative, and sometimes it is the theory which can explain, and it has no counterpart in VSEPR. Right? Bye-bye. See you in the Bend's rule after this, in the 18th lecture on chemical bond. Bye-bye.